to join us today for a technical webinar on Build Tomorrow's Machine Today by Siemens. If you're looking for highly implementable solutions for shorter development time, reliable achievement of development objectives, risk-free testing of innovative machine concepts, higher quality and productivity from an outset, today's technical session on advanced machine engineering has something unique to offer you. Please feel free to send in your questions that will be answered at the end of this webinar. Digitalization is sure revolutionizing the manufacturing sector. To bring all the stakeholders together, our 50-year-old magazine Industrial Product Finder is hosting the 3i Expo on 20th and 21st of May at Nehru Center in Mumbai. A brief introduction on this upcoming event. IPF magazine was launched in 1972 and we have presence in all the major cities in India and a go-to magazine for the heads in manufacturing sector. Since last 2 years, we have started making a digital presence as well, and just grab a screenshot of this number and you could get updates on your mobile phone on daily basis. Apart from the magazine, we also do expos, conferences, seminars, and awards through our magazine. These are the few recent successful events that we have hosted. As mentioned, digitalization is actually revolutionizing the manufacturing sector, and this is a platform where we plan to bring the users, the technology providers together to talk about and bring together an implementable solution of what Industry 4.0 can be. Obviously, you will discover the latest technology, prepare your organization for this transformation, meet the engineering companies who are presenting such innovative solutions, expand our knowledge, and get inspired by what the industry is doing. We have a presenting partner, that is MIDC, Knowledge Partner Automation Industry Association, and a supporting partner, PPNAI. The guest of honor for this year's event is Mr. Sanjay Bhatia. These are a few past chief guests that we have had. The supporting associations for our upcoming edition. And now coming to what we will be discussing in the 2 days of the event. On the day one, that is 20th May 22, we will talk about the future of manufacturing. We will talk about capital cost versus profitability, one of the major reasons that the entire manufacturing sector is thinking, why should we invest in technology? What is the ROI? Here, we will definitely understand what the ROI is from the experts. We will have a focus on automation. We will talk about the case studies. We will understand from the people who have implemented solutions. And we will also have an innovation hub where we see the latest technology. On day 2, that is the 21st May, we will talk about policy intervention, how India can be the next manufacturing hub, and it will be followed by the 6th IPF Industrial Excellence Awards. Through this, we are doing a series of webinars as well, and stay tuned to this update on this soon. Please grab a screenshot and you can connect with Mr. Farid and understand details about the 3i Expo, what to expect, whom to meet on the 2 days. That please mark your calendar, 20th and 21st of May, Nehru Center, Mumbai. With this, let's move on with today's webinar. New demands for customization, smart machines, hyper automation are changing the way machines are designed and manufactured. I now invite the industry portfolio lead from Siemens, Mr. Madan T, to help us explore how digital transformation can unleash innovation in order to develop more connected and extendable equipment at a faster pace. Madan, over to you.
Thank you, Vishali. You can hear me okay?
Yes, I can.
All right, let me share my screen. Let me know if you're able to see it.
Yes.
Coming up. All right. Okay. Thanks, Vishali. Good afternoon, everyone. My name is Madan. I'm industry portfolio lead at Siemens. I specifically look into industry machines and heavy equipment. Thank you for joining us this afternoon. Thank you for spending the next hour with us. Today's presentation is focused on machinery industry and the solutions that Siemens Digital Industries brings to bear. Our presentation today will be focused in two parts. First, I'll present an overview of the market, where the machinery market. And Vishali, is there a, can you hear me, Vishali?
Yeah.
Okay, all right. I heard the recording stop. So coming back, so today's presentation will be in two parts. First, I'll present the overview of the machinery market, the trends and challenges that you as organizations face, and then introduce some of the key technologies that you need for your business to thrive. Following that up, I will present a deeper dive into the advanced machine engineering solutions. We'll briefly touch upon the manufacturing and the service functions of the organizations, but I think our focus will remain primarily on the engineering machines for tomorrow. Moving on. So Industry 4 is something you've heard about a lot. I mean, it was also presented, the tons of events happening. Machinery industry remains the heart of the Industry 4 enablement. It's the core of helping many industries realize the incredible advancements in productivity and efficiency, not to mention being able to highly utilize the advanced technology to the consumer market. So machinery industry forms the heart of every industry that advances itself in the area of digitalization and manufacturing. So many of you work for companies that provide commercial standalone machines, while some of you may be providing integrated turnkey solutions for your customers. Still others may work for companies that are designing proprietary specialized equipment used exclusively for your own company as part of your own competitive advantage. That means you have a manufacturing floor, you're designing your own machines so that you're able to optimize your manufacturing operations and deliver products to your customers at the right cost. What you no doubt are experiencing is how the machines you build are changing, becoming more automated, interconnected, and even intelligent through incorporation of industrial IoT, analytics, and even machine learning. So with that in the background, we'll dive into the topic of digitalization. Now, digitalization is at the center of Industry 4 advent. Digitalization is the key enabling capability that transcends all the trends that you see and which affects our daily lives. So you have heard about all of these terms. It pivots around digitalization as an advancement, which is an enabler for Industry 4. So let's look at a couple of the trends that are obviously impacting the industrial machinery market, which are impacting your business and your day-to-day functions, but also the machinery companies. Digitalization is at the base for the trends for this industry. The first thing is new technologies that companies are required to stay competitive. They must adopt new technologies like additive manufacturing, advanced robotics, generative design, and so on. In your industry is also being driven by customer-driven personalization. That means you're building equipment to a lot size of one. So the days of mass production are gone, and you're trying to customize the machines for specific purpose. And also these machines handle multiple SKUs if they're, let's say, producing products. Smart manufacturing creates the need for intelligent connected machines, which are easier to monitor, easier to optimize. And of course, the fourth trend being globalization. Machinery manufacturers are looking through larger horizons and not just serving the local geography, but also looking at global presence. And with that comes changing business models. Selling assets as a capital assets is kind of slowly diminishing, and then you're looking at product as a service and creating new revenue streams. Right? So these are some of the large trends that are influencing machinery industry. And then let's look at what is a term which is used in digitalization is called digital twin. Now, this is a concept adopted by many software companies, but what is the real digital twin? Many of us use the terms in the way that we support with our product capabilities. Here is an old parable that 6 blind men who had to find out what kind of an animal came to the village, but not having heard of the elephant before. The first one explained that it looks like a thick snake. The second one obviously said it looks like more like a cooling fan filling the ear of the elephant. The third one looked at, explained it as a big trunk of a tree. The fourth man said that it looks like a large wall. The fifth one said it looks like a rope. And the sixth one did say that it looks like a sharp spear. Now, all of them had different definitions of the same subject, which is digital twin, because it is exactly what they are able to bring to the market and based on their subjective experience. But digital twin needs to be really holistic. So let's look at, for industries which are in the business of developing machinery, what does real digital twin mean in the context of your customers, in the context of your own engineering and manufacturing function, and in the context of where your machines are serving, which is your customer locations. Okay, let's take an example. On the left-hand side top, you see a water bottle, which is a consumer product. Obviously, you have multiple SKUs of the same design that's producing that carries different volumes of water, and then the machine that produces that would probably support multiple variants of the same bottle. Now, here is a machine you're looking at, which is checking the formation of the bottle to make sure that the blow molding is formed well before the liquid is filled into the machine in the packaging line. And on the right side, you see the machine, which is, a combination of electromechanic and software technologies integrated to deliver that particular outcome of the product. A key part of your digitalization is leveraging your customer and supply chain digital twins in order to be efficient in the design of your machine's digital twin itself. But it's not only building the digital 3D model of the machine, even if need to incorporate dozens of different bottles and individual customer requirements, the digital twin needs to include simulation to make sure the machine will be durable and support a variety of scenarios and the dynamic conditions it faces when it is in a packaging line, for example. Okay, so that means on the end consumer side, the bottle that you need to produce will be simulated for multiple usability conditions. And on the center, the shop floor will have to be designed to accommodate this machine and work in correlation with the other machines that will be in the shop floor. And independently, the machine itself has to perform the function and to be usable for producing multiple products for your end customer. Now, a true digital twin is something which can take into account all of these scenarios and exhibit an opportunity to deliver a solution which is long-standing and maintain a relationship with your client as well. Now, of course, the digital twin, the way you would be presented to is that CAD software vendors would be talking about digital twin and doing virtual simulation as part of their offering. But what it should also include is the digital twin of production. That means, how do you take this machine to your shop floor and put it together? And then when it comes to operating that machine, the lines of software that becomes part of the PLC programs and orchestrating the entire machine's operations itself. But all the three should come together in a way to represent the comprehensive digital twin to maximize the efficiencies that this advent can offer. Okay, we'll look at the digital twin must include all the product information. That's a given, that the 3D model is not only the part of that. We have discussed how electrical, pneumatics, and piece of software system must be considered while defining the product digital twin. We will discuss about how production digital twin should include the multiple scenarios and the product variants that your end consumer will use this machine for. And of course, for both you and your customer, how should the digital twin of performance be set up so that you're continuously monitoring and optimizing the asset for both your organization to increase the uptime and for the customer to maximize his outcomes. So the benefit of all of these three coming together is immense. That's what companies are looking to address and capitalize on. And the boundaries between these process and systems are beginning to dissolve. So a single vendor delivering all of this comprehensive digital twin is a significant competitive advantage for our customers. So a breakthrough idea does not have to come from the design engineer. It's just likely to come from the manufacturing floor as well, or from the data gathered from the product in the market. And any productivity and production enhancement is not necessarily from the data that's coming from either of these, but it can potentially be all of these areas. Okay. So from Siemens' point of view, while these are our customers' requirements to achieve a comprehensive digital twin, our customers are pursuing different disruptive innovations in multiple functions. They are breaking down the conventional boundaries in their industries. We are doing the same for our solutions using our digital innovation platform. In this age of ubiquitous innovation, we can't afford to continue our thinking in traditional point solutions. The idea is to look at it in a holistic fashion, where we are able to bring together a comprehensive digital twin for design, production, and service. Right, so let's dive a little deeper and then look at what value this can bring before we move down to the second part of our presentation, which is the solution explanation itself. Like I said, at the initial start, we are looking more at the engineering side of things today in the interest of time and the hour we have, and we could look at the production and the performance digital twins in the coming interactions or through one-on-one interactions. So in this integrated digital twin, this helps customers design the machines for tomorrow. There is incredible power in having the most comprehensive digital twin. It means you can innovate and simulate rapidly, bringing machines to market faster than your competition. And the digital twin present the digital twin every part of the manufacturing process. That means even when your machine is in service, you're able to continuously work through the challenges that you face and optimize your designs and machines for your end customers. In this, we help you innovate, keep your innovative edge and cost advantage by gathering and analyzing information from the shop floor and machines in production with our solutions, which are MindSphere and Mendix, and continuous improvement through the information that's available in your digital innovation platform. Only in an ideal world, the first product is right, but your products typically go through multiple iterations. So this closed loop feedback mechanism, not just from your design, simulation, and production shop floor, is key to designing efficient, more cost-effective machines, but also from the field. The holistic approach is only possible with an integrated digital twin offerings. And all of this enabled by the underlying platform, which is Teamcenter. Okay, so we'll switch gears and dive into a bit of detail of solutions that we spoke about trends, we spoke about the definition of the digital twin, and on what it means to realize a comprehensive digital twin. Now we'll move to diving deep on some of the solutions that enable this transformation, and we're focusing more on the engineering space. Okay. Vishali, I hope you're able to hear me okay and the audio is coming in clear.
Yes, yes.
Okay. All right. So now let's break down the building blocks of bringing this machine to life. How do we manage this complexity? How can companies realize a more efficient engineering, more output with the same number of engineers? Machines have also transformed over the years from mechanical to electrical to having significant amounts of software in them. How do we bring these multidisciplines together? How can they reduce the risk and avoid a longer time to money penalties if your machines don't perform as expected? There are liabilities that you have to bear with your end customers, and the compulsions are becoming more and more stringent today. and how can increase control, how can companies increase control of your own processes, right? So that let's look at and dive deeper. Let's look at what are the ways to reduce risk. And of course, let's look at how you can have increased control of your own processes. Okay. Starting with managing complexity, one aspect of managing complexity of the future of machines is multidisciplinary collaboration. The approach enables you to connect the mechanical, electrical, and software engineering data that ends up in a complete machine or a virtual machine on your desktop. It represents the true bill of material of a combination of mechanical parts, electronics, and software. By using machine simulation, companies can take informed decisions and prove predictability through early simulation. Before you build your prototypes, try and simulate as many extensive scenarios as possible, and even perform virtual commissioning to bring down your cost of building prototypes, and more importantly, time. And the third thing being a managed environment to manage the complexities, manage the artifacts that evolve through the cycle of putting together a complex machine of this kind. It enables platform architectures to reuse machine modules for your future machines, enables you to reuse common parts and processes among the family of products, and reuse functional modules of multiple subsystems. Because the future machines you design today, this is not a one-off machine, though you would be personalizing it for a specific client requirement. There are a number of modules that could be reused for your future variants as well. And that's some of the examples that we'll see in the coming slides. Let's deep dive into multidisciplinary collaboration. Let's look at this machine having a very simple door. Now, on a distant view, it will just look like a door that once you close and switch the machine on, it runs up, but it also needs to take into account a lot of safety features, and so that the operators are not able to open it when the machine is in operation. And how would the door behave when a machine is stopped and restarted? What is the gap? What are the safety logics that needs to include it? So there's quite a bit of complexity that goes into just one part of this machine, which is just the door. Okay. Now, 80% of product innovation comes from the combination of electrical, electronics, and software, not just mechanical door with two hinges, right? And that's what we're trying to say here, that how do you bring all of these disciplines together? Now, traditional engineering has always, though there have been quite a bit of electronics and bits and pieces of software in the traditional machines, that they've been independent functions, and they've always come together towards the end of equipment realization. The automated engineering is to have this aspect of collaboration enabled right at the beginning when your concept and moving into detailed engineering. And that gives you the flexibility to collaborate closer and also bring out the machine in the final outcome in a much shorter period of time. Now let's look at what goes into multidisciplinary aspects of the conveyor, which has to handle bottles, which has to identify the shape of the bottles and reject anything which is out of the shape before the bottle moves on the conveyor into the filling station, for example. Okay, there are quite a bit of sensors, actuators, signals, sequences, logic, so on and so forth. Right from the speed of the conveyor, the motor which drives the belt, and the plunger which checks the position of the bottle and its height and this geometrical variation, and then an ejector which pushes out the non-conforming products. Okay, there's quite a bit of aspects that are integrated into it. Let's look at an example here. What you're looking at is selected because it simply communicates the ability of multidisciplinary engineering. It also brings the best options of trying out what is the right speed of the conveyor, to what extent can we maximize the throughput, and so on and so forth. Now imagine that you're in the drawing board of putting together this equipment, and you're able to perform some of these simulations right at the beginning before you go deep into your detail engineering process. In here, you also apply the logic of making sure the geometrical check is done, either by visual or mechanical sensors or optics, so that you're able to perform that. And simulating this early enough in your design process gives you the ability to get right the first time. Okay. This example was selected because it had the best output of bottles in minute. Multiple iterations could be tried, speed, positioning, and all of that. And then you could choose the most optimum design and go about further detailing the equipment. Okay. So one is obviously multidisciplinary simulation, and the concept designer allows us to do so. Now here you can include a combination of not just physical parts and its mechanics, but also include logics and then simulate it accordingly. So easy creation and representation of complex machine concepts. It allows us to do early validation and communication between departments. What the software logic should be to accommodate the chosen iteration, and then utilization of these analysis results for the subsequent downstream detailing, I would say. Now let's move slightly into detail engineering phase. We will look at a customer example, a company called Tronrud Engineering, which creates packing machines, probably awarded as the highest speed packing machines for delivering 20 boxes per minute or 300 bags per minute, which could be modularized to serve multiple use cases. And it uses quite a bit of advanced engineering concepts in this. Now it's enabled through the complete total integration automation offerings of Siemens, and it was also awarded as the best machine in ScanPack in Gothenburg in October 2018. So taking this at the backdrop, we'll look at the multidisciplinary engineering. Let's look at the mechanical engineering part of it, having the flexibility throughout the engineering life cycle of making changes and adopting to limitations that are set forth for the overall design. Now, synchronous technology allows us to not to go back to the part design level and redo quite a bit of work when changes are required at the fag end of the engineering cycle. It allows you to edit any data without concern of how it was built. It makes changes without the regard for creation and where the data came from. Now, in this case, you can use synchronous technology to also edit data which has come from your supplier from a different CAD software, for example. It expands your horizon in terms of any software limitations. It allows you to make changes at any point in time and drive the changes back to your supplier to, let's say, provide the fabrication structure of this machine. So here is the example that we'll see of a machine which is almost in its last stages of design. We are required to move the position of this mechanism right here, which is assembled on the main welded structure. So here we are getting the opportunity to not just go back to where the plate is placed, but actually move the entire assembly and also go to edit the sheet metal part, the fabricated welded assembly, directly without having to go to the base modeling features of the part. Now, in this case, this component could have come from a third-party CAD system, or it could have been inherently built in the NX software itself, but you'll get the flexibility to edit and make changes to design without disrupting the overall other functions. Moving on, let's look at a couple of more detailed examples that here it is required that the clearance hole that's here needs to be repositioned, and accordingly the drawings and the deliverables updated for the vendor to make this for us. And that can be incorporated without having to, because the geometrical edges are moving, your drawings and deliverables automatically update. It's even better if your vendors are using the same 3D model so that we can eliminate the need for engineering drawings. So here additional support is required, and hence we're extending the flange shape right there. We're also trying to minimize the process cost of this component. So all of the unused holes are being removed of a particular dimension. So we can pretty much use the same process engineering data to minimize the cost of making this component. Okay. While we're reusing the part, we can minimize the number of holes and punches that need to be in the part so that we are reducing our manufacturing costs. Okay, so that's what this example is highlighting, to utilize the models as is, at the same time, perform changes at any time in the design without going back to how the features were modeled. Okay, that's the mechanical flexibility. And the user interface is highly intuitive, providing even if users are not highly skilled with certain functionality, it provides an integrated help documentation to refer to any new features that they need to use to stay efficient in their 3D modeling process. Let's switch gears and look at the next aspect of multidisciplinary engineering, which is the electrical design and wire harness design. Now, of course, that the concept of 2D electrical circuits will be done in 2D tools, drawing the schematics really. It could be done in a Siemens offering, it could be done in a third-party tool, or it could come from a vendor. Now, the idea is to bring the vendor information, which is a truly 2D electrical schematic drawing, to facilitate auto routing of 3D wire harnesses and to ensure that there is synchronous exchange of information between both these disciplines and to ensure that you're not missing out on any harness that needs to be wired. And of course, manage this information throughout the iterations that take place in your product design. So here is another example. So here is a controller unit and a 2D schematic drawing. This is just kept as an image for a representation, but this information really comes from a 2D schematic tool. In this demo video, you're going to see that we are directly importing the 2D schematic and facilitating an automatic routing of the wire harness. So let me play this video and I'll highlight what you're able to see. You look at these are the parts of the assembly. There are two connectors in which here we are importing the XML file from the 2D electrical system, and we are nominating which are the two 3D models for the connectors that are being highlighted. And then these two parts will have about 6 wires that need to be routed. You have both options of manual and auto routing. Manual and auto routing. The manual routing where you can choose the way the wire is coming through the cable ties and so on. The auto routing automatically uses wires which are there and then uses the shortest channel path to route. So in here, if you look at the entire 6 wires are auto routed, and in the video that you saw just before, that the green and the amber wire, where green was done manually and the amber wire was done automatically. So instead of performing multiple clicks, you're able to speed up your process of wire harness design. Right now, this benefits enables electrical and mechanical collaboration, bringing together the data between your 2D schematic diagram and two-way communication. That means if there are any misses in the 3D data, you can communicate that back to the 2D schematic diagram as well, so that the electrical engineers and the mechanical engineers are working in unison. You can also reuse electrical information directly from the 2D schematic diagram to create your harness bill of material, and it increases your collaboration between multiple iterations that you do in the schematic as well as in the 3D wire harness design. So towards the end of the cycle, if you have a need to create an additional set of wires, connections, and actuators, for example, you'll be able to edit and push that information back to the 3D modeling environment as well. And then it brings in better manufacturing efficiency because you have chosen the shortest path of routing and also able to visualize how the wires would be fit in, easier to create documentation required for, let's say, nail board diagrams. Okay, let's move to the next phase. Then we'll consider the advent of software. Now, operating these machines does require significant amount of software coding that is necessary. And unlike mechanical and electrical designs, software changes much more frequently. Statistics say it changes 10 times more than the mechanical and electrical designs through the evolution of the product. They are released more frequently. They have much higher complexity, though it's written in lines and codes, piece of programs. It has a lot of variability because you're reusing, again, components of multiple pieces of software programs into the product. And then to get to the better quality, it has a lot of iterations. So while you manage your mechanical and electrical parts in the form of a bills of material, the software lifecycle has its own complexities where one, you're managing it's structured through multiple release cycles, plus maintaining the code base artifacts at the same time synchronizing with the actual bill of material of the product. So which version of the same firmware runs which release of the machine. And if you're making multiple variants of the machine, that there will be multiple versions of the software which would be applicable for different configurations or as-built structures of the machine. And that adds to a significant level of complexity. So what we can do with the software management piece, that the application lifecycle management capabilities of the platform, is to not just give you product traceability with Teamcenter serialization and as designed as built configurations, but also at the software level provide traceability, that which firmware of software runs in which version of the hardware or the equipment. And then it manages your reusability of your software artifacts in a very inclusive and collaborative manner. Okay, so here is a representation of looking at the mechanical BOM, the electrical BOM, and the automation software, which goes into the final product. And traceability is ensured through this multiple disciplines. Okay, I do assume there are questions coming in. We'll address them in a short while. Right, so here is an example of how multidisciplinary engineering has helped a company in South Africa called Burkhardt Weber, which makes industrial machines. They migrated from a third-party CAD solution, which was just truly only doing the mechanical design for them and not just enabling this collaboration. They moved to NX portfolio, and then they were able to reduce the number of CAD licenses needed to engineer the machine by 30%. That means less number of designers were able to accomplish more. They improved 20% of their component data reuse enabled by Teamcenter, so they could search and reuse parts, bringing down the overall cost of engineering and manufacturing itself, and again, passing on the benefits or increasing profitability in some cases. Massive model creation and editing with the same hardware, because it was able to handle large amounts of data with necessary graphic intensive application. And then concurrent design between electrical and mechanical increased their overall time to manufacture. Let's move to the next step of simulating the machine. Now, this is a lot of unique capabilities that you may not see or you may not have seen in the past. And here's, let me explain it in greater detail. Now, obviously, you saw a very brief simulation in Mechatronics Concept Designer of the bottles being rejected if the shape of the bottle is inaccurate. Now let's look at the realization of the machine. That here is a simulation function called 1D simulation enabled by our simulation portfolio, which allows us to simulate both the mechatronics piece of it and also include the multi-physics simulation that can be done earlier in the design phase. Extensive libraries containing hydraulic, pneumatic, and software attributes can be used. So you're not just designing iterations of the mechanical components, but a combination of all the three. And this simulation is critical to choosing the right iteration for you to go about doing the detailed design. And once you realize the detailed design, we move on to 3D simulation, where you could also simulate the functions and the dynamics of the machine, but also quite a bit of structural, thermal, and dynamic simulation, all included in some of the integrated capabilities. So the device going up carrying a set of components. Obviously, this is a animation which is extrapolated, but this is the kind of load variations that it's experiencing. And then strengthening the carrying platform can optimize it after correction. So 1D simulation at the early stage of the engineering cycle, 3D simulation when you have already realized 60-70% of the design. And then here, testing with sound cameras, acoustic cameras, where once you build a prototype, you are able to do some level of advanced testing and optimize the noise levels that the belts and the motors and the hydraulic cylinders create. So that is something which could be done towards the prototyping stage of the product as well. Okay. Now, virtual commissioning is another subject that you realize that you're designing the machines with mechanics, electronics, and software. And you also need to simulate all these three working in unison You can obviously do that when you build a prototype, but any changes that needed in the mechanical structure, it will be too late to incorporate. So the idea of what we call a software in the loop can be done right at the design stage or through the evolution of the design. That means the PLC program that goes into the PLCs to operate the machine for a specific speed and logic could all be simulated virtually before you physically bring together a prototype. That means at the automation level, the PLC programs could be simulated directly by sending it to the PLC, which is called hardware in a loop, or it can be sent to a SIMATIC controller, which is software in the loop. It will give us errors and any logics that needs to be reworked to ensure a smooth functioning of the machine. So let me show you a small simulation here. So now here with the CAD data and the logic that's built with software and the controller, we are using a HMI to simulate the logic at the software level. Let me play this video for you. It brings out all the potential errors in the logic and the way the system is programmed, and you get to go and quickly overcome those bottlenecks. For example, safety door was opened when the belt was in operation. Could be a issue with the logic, then that could be edited and the program can be updated instantly. And in the hydraulic cylinder, no pressure is detected. That's an issue that it's highlighting in the virtual commissioning simulation. That can be overcome as well. And likewise, so it highlights all the challenges potentially. It is only done when the physical machine is realized, and quite a bit of iterations happen post that. And here we are able to do that at the early stage itself. Right. So in summary, we can avoid multiple machine issues from mechanical design or via risk-free simulation. So when you realize the physical prototype or you're building that custom lot size of one machine, you're very, very certain that that machine is going to tick mark most of the test situations and avoid a lot of lengthy changes doing planning and commissioning to fulfill the requirements. The complexity increases significantly if you're building a line, for example. Okay? And overall, it brings down the time needed for commissioning by up to 70% because you're virtually simulating quite a bit of iterations right on your desktop as opposed to doing it physically. Okay, so here is a quick picture of how working with multiple controllers, we graduated this customer of this machine into a single vendor offering. You are aware that in addition to the software technologies that we're talking today, Siemens brings in a large hardware portfolio, right from the PLC level to the controllers and the SCADA systems and so on. So sticking to one vendor, and Siemens has a potential benefit in that area to kind of bring a total solution. Quite a bit of virtual commissioning activities could be done digitally right during the design phase itself. So bringing down the overall cost and time of your engineering cycle. And of course, a complexity of this machine needs to be on a digital backbone, giving you the ability to collaborate efficiently, but also transform that information to your downstream manufacturing. Let's deep dive into a couple of key aspects of the managed environments. Now, the overall functions that you saw has three business models that you probably configure a platform designed to order. That means these packaging machines could be configured for different applications, bottles, chocolates, bags, and so on. It could also be situations where you need to engineer to order. That means a custom equipment has to be engineered specifically for a use case. And the idea is to support both business models using the option of a platform. A platform is nothing but which commonizes your multiple subsystems and gives you the ability to build variants by increasing the ratio of reuse across multiple machines, so as to bring down the cost of carrying multiple part numbers in your enterprise. Okay, so this is the outcome, increasing your product variants by maximizing usage. So, and we have discussed at length that product complexity is increasing, customers are demanding personalized equipment, and you need to go to that last mile to personalize the equipment for that specific function. And if you're doing a line, there is added complexity, and offer a variety of options with the right cost, so that there's no additional modules which is taking up the cost of the equipment, and complex network of features that constraints intertwined into the product content, simulating multiple scenarios. In this case that we discussed earlier in the presentation, that how can we measure the geometry of multiple sizes of bottles, from half a liter to maybe a larger sized container, for example. And that's the kind of modularity we can bring in with the features that we have discussed so far. So this team center environment provides a single disciplinary environment to manage all of your artifacts. It acts as a backbone for not just design data, but all of the documents and other artifacts which go with it. It enables commonality and reuse. More importantly, it brings in discipline into your engineering, revision management, file management, security, who accesses what, when, and so on and so forth, and manages all of the integrated requirements from requirements document to project plan and till the final efficiency of the program itself. This is a quote by Winston Churchill, that those who plan to do better than those who do not plan. Not that we always follow what we plan, but a little bit of planning enables us to be more efficient than the ones who do not plan. So plan is necessary to structure the course of action within the restrictions of time and the available resources. It certainly, following some of these methodologies, enables you to get there faster. Coming to the phases of planning maturity, they start off with a foundational environment, which is typically, you can call it phase one of establishing a single source of truth backbone, which is to monitor and control the status of the phase gate process, typically a phase one of a product lifecycle environment deployment. And of course, the gate process, can be improved. The maturity levels can go up by adding multiple phases and ending at the product and program management outcomes. And this maturity will give you significant advantages to design machinery of the future. Okay. It manages the complexity, not just design data, but manages all of the artifacts, and allows you to reuse content, again, not just in designs, but other documentation specifications that would go into designing your past products. It helps enables concurrent design and so on. And the added capabilities, once you establish the vaulting backbone, it includes integrated change management. It also acts as a window of environment to take the data seamlessly to manufacturing. So you can avoid emails, shared drives, all of those methods that you traditionally follow if an enterprise backbone is not set up. It's highly configurable to suit different scale and complexities of businesses. So it could support a very small design and engineering environment of, let's say, 10 or 15 people, to supporting very large multidisciplinary, multi-location engineering teams situated across the globe. Kind of support the design anywhere, build anywhere approach. Right. So overall, the change management improves your efficiency of incorporating change, supports the CM2 change management process. So all of the changes can be audited. You can bring down the number of changes that you do in an organization, because you have the wealth of information on what are the reasons that the past changes have occurred. And then for all the product assets. So for example, if there is a schematic, the drawing change, what implications does it have on the 3D models? And that will transcend into what changes you need to do in downstream manufacturing, both for mechanical or the wire harnesses or the electrical parts. Okay. So in summary, I'm just summarizing the three main advantages of digitalization with whatever we have spoken. Remember, we are focused only on the engineering side of things, realizing the product with its true definition of digital twin, doing multidisciplinary design, managing it through a single backbone, so that that platform facilitates change, configuration, and platform and program management. So it makes your organization more efficient, reduces the risk of timelines. Virtual commissioning significantly brings down your need for building prototypes, as well as the time required for commissioning of assets. And then, of course, it enables seamless reuse of information through your organizational backbone. Okay. And why Siemens? Because Siemens brings in the most comprehensive digital twin. The examples of what it means, we spoke right early in our presentation, that it's not just a simulation twin or a 3D model twin. We represent digital twin its true potential, that is across the evolution of the product through engineering, manufacturing, and service, and then enable seamless value that's created out of the comprehensive digital twin. You saw some examples of it. We can go down to the aspects that we cover in the production twin and the performance twin as well. But maybe if that's an area of interest, we could connect again and go through that detail. So please do put it in a chat or send us an email through the contacts that we will present at the end if you're responsible for some areas beyond what we have covered today. Okay. And of course, as the saying goes, Siemens is not just a software organization. It has this 150 years of heritage of engineering and manufacturing. We pretty much eat our own dog food, so to speak. That means we deploy our own solutions in our manufacturing plants, and hence these are proven to be directly adopted by organizations who are looking into the path of digitalization. So I do believe I finished reasonably early. My apologies if I've been extremely fast, but the benefit is that gives us quite a bit of window for our question and answers. So I'm open to taking some questions while I also share my contacts if you need to talk at a different time.
Thank you, Madan. That was a very interesting presentation.
Sure.
We have a few questions. Let me start with the first one.
Mm-hmm.
How the sequence of design, mechanical, electrical integration, one software. Any simple example to understand the whole concept?
Okay, let me go back and look at the question.
It's in the chat box, if you can.
It's in the chat box, yeah. Okay. Yeah, I see about 4 questions. Let me. Sorry, can you read the question for me again? I don't seem to be able to see it.
The sequence of design, mechanical, electrical integration in one software. Any simple example to understand the whole concept? So probably the design, the sequence of design. Is there any simple example you can share?
Sure. So the mechanical design happens in the NX portfolio. The electrical design happens in dedicated tools which are capturing the schematic design. That's the 2D PCB or PNID diagrams, if you will. There is seamless exchange of information between the electrical and mechanical component. In the electrical schematics, you are representing connectors, pins, and what wires need to be connected where in a 2D schematic form. That is where your concept of electrical design is happening. And that is brought into the 3D environment, which is under Siemens NX portfolio, which will take, let's say, if the wire harness needs to be having 150 connections for these machines, right from the power on switch to the controller systems to the actuators and the hydraulic equipment, that all of that information is captured in the 2D schematic. We use a simple XML export import functionality. In the first video that we saw, where the wire harness, second video, where the wire harness auto routing was happening, we imported an XML file that becomes the input from the electrical designer to the mechanical designer. And the mechanical designer takes that as an input and start routing the wire harness. And then the nail board diagrams are created right out of the NX portfolio. Now, software artifacts are simulated and logic is captured in the 1D simulation and the mechatronics concept designer. And then software team can design individual pieces of software which could be done through different programming methods, and the artifacts brought back in to simulate the behavior of the machine in the same environment. So we don't help create all of the functions, but we integrate all of that in the central platform. That's the examples that you saw, representation of a true bill of material of software, mechanical and electrical parts. I hope I've answered the question. If not, please put in a comment, then we can just talk one-on-one.
Thank you, Madan. Mr. Abhay Deshmukh thinks that, this was a fantastic presentation. However, ROI and learning curve are two important concerns.
Sure.
What are your thoughts on that?
Yeah, I mean, every customer who makes this transition is really looking at the outcome that they will generate out of such digitalization investments. So it is true that you will not put the money on these initiatives unless you're seeing the final outcome, at least either by looking at what your peers have done or going through due diligence of how we can deliver an ROI. So we're happy to work through with your organization and capture the current processes and then, work through a potential ROI based on our past experience. So it's true that ROI and outcomes are key important aspects, and we always take that into account.
We have another question. How important are sustainability and safety for machine builders? And how is Siemens helping machine builders address these issues?
Yeah, so sustainability and safety are definitely regulations which are becoming stringent in your machines. Obviously, these machines have a much larger life cycle. That means they operate for 20, 30 years in its final listing, but there are regulations to ensure that there is a very high degree of recyclability. That means you can take an old equipment, rip it apart, and then repurpose it for quite a bit of function. So we have some solutions which can monitor the usability of restricted substances through the evolution of the product, that the kind of materials you use. So the material libraries give you a track of restricted substance usage in your bill of material. But when the product reaches its end cycle, what is the level of recyclability also can be captured in the environment. Maybe that's a topic that we haven't covered today, but happy to deep dive into the capabilities that we bring. And of course, in safety, we can do quite a bit of virtual simulations right here, even if that includes people in the process. So the machine is operating at high speed. You have to have the safety door locked at all times when the machine is on. All of that logics you're building in. And if you have to simulate person fatigue, we have process simulation and plant simulation solutions to address that space.
The next question we have is about the workforce. The new features and software advancements mean upgrading the current shop floor workforce. And how do you think Indian workforce is prepared for this new advancement?
Yeah, so I think skill of using some of these tools is certainly key. We obviously have a structured enablement program once our customers acquire some of these softwares. But even today, if you look at, you may not be doing all these functions within the organization. You may be outsourcing parts of your engineering activities traditionally because you've come up as a mechanical engineering organization. But the future machines are going to have a strong mix of all three. So obviously, skill upgrade and bringing in new expertise is important at this stage. But we can work with you through a cycle of how we can get there, and to begin with partners who bring in that skill sets, and then slowly build that capability in-house so that you could be most optimized in your engineering function.
We have one more question.
Sure.
About the machine design process. The machine design process can be modularized dramatically. Can you highlight on its integrity with the current available systems and machines?
Okay, obviously when we go to, let me see if I understood the question right. So the machines represent quite a bit of modularity. how would some of these new environments exist with your traditional engineering methods? Yeah. So two areas that I would like to point out. One is that if you paid attention to one aspect in the mechanical design, when we were talking about multidisciplinary design, we spoke about synchronous technology. So even today, if you're using NX, that data comes in seamlessly into this modern environments. If you're using non-NX third-party CAD systems, we have the ability to import that in a solid format. But the synchronous technology still allow you to edit, modify, and reuse that content, which you may have designed 10 years in the past. So that means we will coexist with the systems and processes that you follow today. We may have to sunset some of the application usage and transition into these suites so that it provides faster outcome. The Roki example that we saw was where they moved from the old system, upgraded to NX, where they could do multidisciplinary design, and they were able to bring down their 20% improvement in reuse of parts, 30% reduction in the requirement of CAD licenses. That is significant justification for small change, but I think the primary idea would be to coexist with the complexities that's already there in your organization.
Thank you, Madan. Those are the questions we have. Is there, okay. Do you want to summarize your presentation?
Do you have the ability to open a channel if somebody wants to ask a question, or are all of them muted?
No, we've taken all the questions that were asked.
Okay. So if anybody has any further questions, feel free to put them in the chat. And I wanted to thank you for your time. In summary, today we discussed what the future of machine industries would be. Industrial machinery is a strong enabler for the advent of Industry 4. So whether you are building machines for CPG industry or pharmaceutical or automotive or any of these verticals, machinery industry is at the heart of Industry 4 transformation. So you would be the pillars of enabling this transformation. And for you to be able to sustain the need from your markets, using some of these advanced technologies is imperative. Like I said, we covered only the engineering piece of the functions today. We could talk about what it means to make these machines faster in your shop floor. We could also talk about what it means to your business if you're monitoring these machines real time that are running in your customer places. But if you have interest in those areas, put in a comment or send us back your feedback. We would be happy to dwell into those areas as well. And I hope with whatever you've heard today, that you have a couple of takeaways to discuss with your internal colleagues and then come back with how we can partner together with you. So that I would like to thank you for your time. And we'll wait for a couple of minutes to see if there are any further questions before we close the session.
Thank you so much, Madan. It was very interesting, and though we have a lot of requests about people wanting to read more about this and wanting to understand this, I would like to share with them that we will send a follow-up emailer with them with all the details so that they can browse through the content and understand in detail. And you can also see Madan's email ID on your screens currently. So if there are any questions, you can write to him directly. Yes.
Sure. And the session is recorded as well, and you'll make the recording available if you would like to share this information with your larger audience within the company before we could have our next meeting if needed. Yeah.
Thank you. Thank you.
All right. Thank you, everyone, and have a good rest of the week. Good day.
Thank you. Thank you, everyone. I hope you had a very interesting session. And please do keep in touch if you need any more details on this.